everyone, I am Madam Rosmaya. Welcome to my YouTube channel. So in this video, we are going to discuss on past year's STPM physics essay question. Topic: sound waves, sources of sound. Okay, first question 1A. State two necessary conditions for the formation of standing waves. So the marks given is 2 marks. So the two necessary conditions can refer to the animation here. Okay, the animation shows two waves moving through a medium in opposite directions. So the blue wave is moving to the right, and the red wave is moving to the left. So the result of the interference of the two waves above is a new pattern known as a standing wave pattern. Okay? You can refer to the black wave here. So this is the standing wave form. So the two necessary condition is the first is the two waves must have the same frequency, and second, the two waves move in opposite direction. So you get 2 marks. Okay, question 2. Question B, 1B. A standing wave on a stretched string is represented by y equals to 3.0 cos 0.10 pi x sine 85 pi t, where y and x are in centimeters and t is in seconds. So determine the distance between two consecutive nodes, 3 marks. And question 2, calculate the velocity of the wave which form the standing waves, also 3 marks. Okay, to determine the distance between the two consecutive nodes, okay, you must know what is meant by node. So example, in this standing wave, okay, so the node is this point. Okay, so node is position on a standing wave where the wave stays in a fixed position over time because of the destructive interference. And then this is the node, and the antinode positions on a standing wave where the vibration with maximum amplitude. Okay, this is antinode, this is node. So each of these loops, okay, form is about is a 1/2 a wavelength. Okay, so you can see here 1/2 of a wavelength. So this is here to here is a one complete wavelength. So if cut half, so here means between two consecutive nodes will give you 1/2 a wavelength. So in mathematical form we write half lambda. So lambda is a wavelength. So we are going to determine this lambda. Okay, then we can determine the distance between these two consecutive nodes. So to determine lambda, so we use the equation given, the equation of the standing wave given. Okay, from here we compare with the general equation of the standing wave, which is y equals to a cos 2 pi x per lambda sine omega t. So we compare 0.10 pi x equals to 2 pi x per lambda. Okay, then we can cancel out pi x. So we can solve for lambda. So lambda is 20 centimeter. Okay, 2 per 0.10 give you 20 centimeter. So this is lambda 20 centimeter. So we substitute into half lambda here. So half of 20 is 10 centimeter. So this is the answer. Okay? So distance between two consecutive nodes is 10 centimeter. Okay, next we do question 2. Okay, question 2, we are going to calculate velocity of the waves, okay, which form the standing wave. So we use v equals to f lambda because lambda calculated from 1, okay, and then v is what we are going to determine, and the frequency we can use this relationship. Compare these two the two equation, okay, this equation given with the general equation. So the sine part, okay, 85 pi t equals to omega t. Okay, 85 pi t equals to omega t. So t can be cancelled out, and then we can substitute omega equals to 2 pi f, and also pi can be cancelled out. So we can get f, frequency. So frequency is 85 per 2. Okay, So we substitute into this equation. F is 85 per 2 and lambda is 20 centimetres. So convert to meter. So we calculate, we get V, velocity of the waves is 8.5 meter per second. Okay, so this is the answer. Okay, so you get 3 marks here. Okay, next we go to question C. A long tube which has a tap fitted to it and filled with water is shown in the diagram below. So this is the diagram. So a long tube here, filled with water, then here a tap, and this is a tuning fork. So the tuning fork here of frequency 512 Hz is sounded above the tube as the water flows out slowly through the tap here. Okay. Then the first loud sound is heard when the length of the air column is 15.7 centimeter. And as the water continues to flow out, a second loud sound is heard when the length of the water of the air column is 48.1 cm. Okay, so this the frequency of the tuning fork is 512 Hz. Okay, and then the tap is open, so the water flow out. So the first loud sound heard, let's say this original length. So the first loud sound heard when the length here becomes 15.7 cm. Okay, so then the second loud sound, okay, the water continue to flow out from the open tap here. So the second loud sound heard, L2 is equals to the 48.1 centimeter. Okay. Okay, now we go to the question. Sketch the stationary wave in the tube when the loud sounds are heard. Okay, these two position of the water. So the stationary wave, how to sketch the stationary wave in the tube. Okay, the first one is the okay, imagine that this is the vibration of the air molecules inside the tube here. Okay, so the loud sound heard is where the resonant occur. So you can imagine, use the analogy of the string wave. So if we draw the air molecules wave, so it's hard to see to compare the node and antinode. So better we use the analogy by drawing the what you call this, a string wave. Okay, we can draw analogy using the string wave. Okay, so this is the first resonant occur. Okay, the stationary wave in the tube when the first loud sound heard. Okay, the second one, if you imagine here the tube like this lah, the first vibration of air molecules here shown here. Okay, so this is node, this is antinode lah. So at the point above the water here is fixed point, node, always node. Here is always node. So at the open end is always antinode. Okay. Okay, next for the second loud sound. Okay, so this is the first antinode, so means it happened at the second antinode. So this is the stationary wave can be drawn. Okay, so if you use vibration like this lah, so this is the first antinode, this is the second antinode. So we have two nodes and two antinodes. Okay, so to form the stationary wave. Okay, next done for the question 1 to sketch the stationary wave. Okay, so the second question is the meaning of end correction. So what is meant by end correction? So end correction is the distance from the end of the tube to the antinode above the tube. So let's say this is the end of the antinode. So from the end of the tube, okay, to the above antinode of the tube. Okay, so this part lah. Okay, this part is the end correction. Usually we use symbol C, okay, for the end correction. Okay, next question 3, C3. Determine the velocity of sound and the end correction for the tube. So now we are going to determine the velocity of sound and the end correction of the tube. Okay, so we use V equals to F lambda because frequency is given here 512. So now the problem is we are going to determine lambda, the wavelength. So for the wavelength, we use these two length of the resonant occur. Okay, length of the tube where resonant occur, 15.7 centimeter and 48.1 centimeter. So the first one, we include the end correction. Okay, end correction is this part C. So that's mean the length is C plus 15.7 here, L1 plus C equals to the wavelength form here is 1 per 4 lambda. So how you know 1 per 4 lambda? Okay, the analogy is this is for 1 lambda, 1 complete 1 lambda. So for the half lambda is here, center here. And 1 per 4 lambda will be here. Okay, so this form of wave stationary wave here is in the form of half 1 per 4 lambda 1 per 4 lambda. So 1 per 4 lambda equals to L1 plus C, which is L1 is 15.7. So we substitute 15.7 here. Okay, so this is first equation. So next, second equation for the second loud sound heard. Okay, second loud sound heard form 3 per 4 lambda. Okay, so this is half lambda, so add another 1 per 4 lambda. So this is the form of 3 per 4 lambda. Okay, the shape of the wave stationary form here is 3 per 4 lambda, so equals to L2 plus C. So L2 is 48.1 cm. So we substitute here 48.1 cm plus C. So we get two equation. Okay, equation 1, equation 2. Then we can determine lambda and C and correction using simultaneous equation. So use simultaneous equation, we can, equation 2 we can do, what we can do is equation 2 minus equation 1. So 3 per 4 lambda minus 1 per 4 lambda, we get half lambda. And C minus C is 0, okay, cancel out. So 48.1 minus 15.7 is 32.4. So we solve for lambda, okay, we get 64.8 centimeter. So we substitute into here, so we get velocity of the sound. Okay, the question asks for velocity of the sound. So 3.32 times 10 to the power 4 meter per second. And the end correction, so we can substitute the value of lambda here into one of the equation, either equation 1 or equation 2. So let us choose equation 1. Okay, 1 per 4 lambda equals to 15.7 plus C. So we substitute lambda into here. Okay, 64.8. Then we get C 0.50 centimeter. So this is the answer for end correction for the tube. Okay, so that's all for the question. Okay, thank you for watching.